Hey everyone, and welcome. Get ready because we are unpacking something truly mind-bending today. In this explainer, we're diving deep into the OWL Academy's SHD-CCP GitHub repository. We are looking at a fundamentally new way to process information, specifically the 64-bit Fractal Processor. It completely challenges everything we currently know about how computers actually think and handle data, and it proposes a model that could honestly rewrite our limits on computational speed.
So I want you to think about this. What if your computer didn't process data in a straight line, but actually tied it into a knot? Since the very dawn of modern computing, we've essentially pushed bits of data down straight linear highways. It's the method we all know, and it's what we rely on. But think about folding a map. Instead of dragging your finger all the way across the paper to get from point A to point B, you just fold the paper so those 2 points touch instantly. What if the secret to infinite computational scaling isn't building a faster highway, but fundamentally changing the geometry of the map itself? What if data could literally be braided?
To unpack all of this, we have a really fascinating roadmap ahead. We'll kick things off with beyond traditional computing, then we'll look at the Twistor Mechanism, explore the Fractal Computing Pipeline, see scaling up the system in action, and finally, wrap up with high-performance networking. All right, let's jump right into Section 1, Beyond Traditional Computing. To truly grasp why this is such a game changer, we first need to understand the limitations of how we normally compute. On one side, we have the traditional von Neumann architecture. This is the linear processing model running basically every single device you own right now. And it suffers from a massive fundamental bottleneck. The CPU and the memory are physically separate. Data is just constantly traveling back and forth in a straight line, which creates a severe, totally unavoidable traffic jam when things get busy. Now, on the flip side, we have the fractal processor. This architecture abandons the straight line entirely. Instead of brute forcing data through that single congested highway, it relies on geometric computing to achieve infinite scaling. By mathematically folding data into topological knots, the processor can skip the highway altogether, allowing for calculations that would instantly bottleneck a traditional system. The actual reality of this implementation is called SHD-CCP, which stands for the Symbolic High-Dimensional Context Compression Protocol. Simply put, it's a software-defined 64-bit fractal CPU environment. But the real surprise factor here? This deeply complex theoretical math isn't running on some multi-million-dollar quantum machine locked away in a secret lab somewhere. Nope, it's built right on top of standard .NET 8.0 C# infrastructure. It's a completely accessible software protocol that brings theoretical, sci-fi level physics right into our modern, everyday programming environments. Moving right along to Section 2, the Twistor Mechanism. So this brings us to how data physically enters and behaves inside this fractal system. Enter the Twistor Mechanism. You can think of this as a tuning engine that physically forces data streams to phase lock into what's called a stable Triple Trefoil Quaternion Equilibrium. I know that sounds incredibly dense, but think of it like tuning 3 different strings on a musical instrument. If you tighten them perfectly, they vibrate in absolute harmony. Well, the Twistor Mechanism does exactly this with data, locking it into a physical mathematical shape. We aren't just saving a flat file to a hard drive anymore, guys. This mechanism mathematically binds the data into holographic storage. Imagine weaving literal threads together under precise torsional stress. The data gets split into 3 core streams to form a 3-under-1 trefoil knot. Step 1 is path A. This represents the math, and it winds exactly 1 time to dictate the orientation and logic of the data. Step 2 is path B, which represents the semiotics. This one winds 2 times, dictating the topological surface and meaning, so essentially creating the codex. And finally, step 3 is path C, the physics, which winds 3 times to dictate the field strength, spin, and energy. By combining logic, meaning, and energy, the data isn't just stored as a simple 1 or a 0 anymore. It becomes a 3-dimensional geometric shape, locked together perfectly by that tuning engine. Okay, let's look at Section 3, the Fractal Computing Pipeline. Let's move from all that macro theoretical physics down to the micro, grounded C# software engineering that actually makes it tick. Because despite how esoteric and abstract these concepts of twistors and quaternions might sound, the execution in the software is a ruthlessly efficient zero-stall pipeline. The Fractal CPU operates in a strictly lock-free, perfectly parallel manner. In everyday computing terms, a zero-stall pipeline just means no processing power is ever wasted waiting in line. There are literally no red lights. Every single operation flows continuously without a single pause.
Let's actually trace the journey of a single point of data as it moves through that relentless pipeline. Step 1 is the sample phase, evaluating the x, y, and z coordinates of the trefoil equation. To do this, it uses AVX 512 aligned arrays, which essentially act like a massive mathematical snowplow, processing huge chunks of numbers all at once instead of one by one. Step 2 is the pack phase, which converts those physical coordinates into unit quaternions, a very complex four-dimensional number system. And finally, step 3 is Serialize. It uses a technique called tree folding to safely pack that geometric shape securely for travel, appending a checksum and blasting it across the network's ring buffer. So it's sampled, packed, and dispatched in this beautifully orchestrated flow.
Which leads us perfectly into Section 4, scaling up the system.
Because a pipeline this incredibly efficient is built to move massive amounts of data, let's turn this into a story of scaling. Imagine starting on just your local laptop and a standard DevLab environment. With just 4 cores, this architecture comfortably handles 10,000 complex shapes a second, with almost zero latency. That alone is highly respectable. But throw this onto a deep compute workstation with an 8-core processor and a dedicated GPU, and suddenly you are processing 1 million shapes a second. Take it even further to a galactic sync cluster, multiple nodes networked together, and you're achieving a jaw-dropping throughput of over 10 gigabytes per second. It builds incredible momentum, scaling dynamically and horizontally across whatever hardware you give it. Let's actually pause on that middle milestone for a second. 1 million. 1 million complex geometric shapes processed every single second on a single workstation. This massive leap in performance happens because the software fundamentally unrolls its computational loops. It heavily utilizes SIMD vectorization. That's single instruction, multiple data. If standard processing is like carrying 1 box to a truck at a time, SIMD is like using a forklift to carry 4 boxes at once in a single clock cycle. Combine that forklift with offloading the heaviest math directly to an NVIDIA GPU, and you achieve some seriously explosive speed.
And finally, Section 5, high-performance networking.
Now you might be wondering, with all this incredible speed, how does a system moving 10 gigabytes of mathematically bound data a second actually avoid crashing? Well, in a standard software environment like C#, you have garbage collection. Think of garbage collection like a city randomly shutting down its busiest highways right in the middle of rush hour just to sweep up trash. It pauses the whole system. But in this fractal architecture, even a microsecond pause would instantly unravel that perfectly tuned mathematical knot of data we built earlier. So strict networking layer patterns are absolutely mandatory to prevent that garbage collection pressure from destroying the delicate geometric resonance of the entire cluster.
To achieve this perfectly balanced, crash-free network layer, the system relies on 3 really rigorous techniques. First, zero-copy pipelines completely bypass standard socket allocation. Second, buffer pooling uses custom ring buffers to instantly recycle packet memory. And third, lock-free concurrency replaces standard locks with atomic operations, so threads never, ever get stuck. The brilliant overarching theme here is that they achieve impossible speeds by never allocating anything new. It is a completely closed-loop system where memory is endlessly recycled without ever stopping the processor to ask for more resources.
We have traveled all the way from the topological theory of twisting data into nuts, right down into the trenches of C# memory management and infinite scaling. And honestly, it leaves us staring at a fundamentally different computing paradigm. So, what does this all mean? Will geometric processing completely redefine the physical limits of hardware, or is this just the very beginning of a much larger software revolution? The SHD-CCP repository provides a really compelling proof of concept that the boundaries of computing might not be linear anymore. They might just be geometric. Thank you so much for joining me to explore this incredible architecture. Keep questioning the limits of what's possible, and I'll see you in the next explainer.